Welcome everybody. My name is Chris Perry. I'm here to talk to you about test-driven development. So I want to start by talking about the development process a little bit. Depending on where you work, you might have some process that looks kind of like this, where you have software engineers whose sole job is to write code. So they develop the code, and you have a QA guy that kind of does some manual testing. He'll have a bunch of different devices, and he'll have a big spreadsheet full of test cases that he'll work off of, and he'll poke around in the app and try to break stuff. And then he'll come back with bugs that you have to fix. And if you're lucky, the third row there, you might have some test engineers that are employed that are going to write some automated testing, maybe some UI automation test framework that they're doing, and they're kind of writing some tests that'll kind of automate what the QA guy does, poke around in your app and make sure everything's working how it's supposed to, kind of on the outside. Or you might be a little bit more unfortunate and have something like this where you don't have a test engineer, so the software engineers might be kind of doing some of this testing magic and doing some of the automated testing instead of the test engineer, and the QA guy's doing the manual testing. So what's the problem with this? It takes too long. Or what about when you get the bug and, yeah, well, you kind of forgot what you wrote. It takes a long time to track down the bug. You got to open up the debugger, and you got to kind of find it. If there's a stack trace, you can kind of follow that. Oh, no pointer exception on line 58 or whatever of this class, so I know exactly where to look. Or it might be something a little more complicated. So you got to spend a lot of time in the debugger running on the actual device. Also, when you're getting bugs back from your QA guy, you might fix a bug and reintroduce or introduce a brand new bug. So, you know, you take one step forward, 2 steps back. You fix a bug, you create another one. You fix that one, you might yet create another bug. The quality kind of comes after you've written the code. So, testing is not like frosting. This is where people write code after they've written the test, and there's, like I said, there's no quality baked into the cake, essentially. So a better model for development would be something like this, where you're constantly testing and developing and refactoring your code and making constant check-ins. And this becomes part of your, so it becomes part of your process when you write your code. You can have these tests run as part of your continuous integration environment. Do you guys, everybody knows what that is? You have something like Jenkins that's doing your builds and running all your tests every time there's a check-in. So you're being constantly reassured that the code you're writing isn't breaking anything, and that it actually builds so that when people pull new code, they're not all of a sudden broken. So with this model, it becomes, instead of the QA guy or the test engineer's responsibility, it becomes the developer's responsibility to write all the unit tests. This is different from the UI automation tests. These will catch different types of bugs than those type of tests will. So the tests actually become part of the process of writing your code. You don't write the code first and then afterwards, as an afterthought, write your tests. It's part of the process of writing your code. So what are some problems with testing afterwards? So if you have a code base and the code is working, you know, you could poke around in the app, oh, it looks like it's working. Who cares what it looks like underneath? You know, you might have this beautiful house, and inside there's a hoarder living there, and you can't tell by looking at it from the outside. So you're very unlikely to change the code base, and management has risk factors that they assess, and they might not want you to change it either. From their perspective, they'll usually just be like, well, it works. Why change it? Let's just keep plugging away and adding features. So when you write tests after the fact, if you even write tests, all of your effort is going to go into writing the tests, because the code that you write will not be testable. It's because the testing part wasn't baked in to begin with. So we'll see some more of that in a bit. And then, oh, here's another problem. So if you are adding refactoring tasks to the backlog of things to do, this is a sign that you are not doing test-driven development. Refactoring is a part of the process. So the saying goes for test-driven development that you write a failing test first, then you write a minimal amount of code to make that test pass, and then you refactor your code, and you just do this in a cycle. The saying is red, green, refactor. So red is the failing test, green is the passing test, and then you refactor to make the code right, get a little bit better structure underneath. And the code base continually evolves over time. So this is more of a emergent design rather than designing up front some overarching architecture imposed on top of the code and then trying to slam in implementation details that are spaghettified through the entire piece of software. That becomes very hard to test. It becomes very hard to add to. When there's bugs, they pile up, and it makes you take a long time. So one place that I worked that I will not mention, we did not write tests, and we would have these really long time cycles for QA, where we'd just be in development mode, just cranking out features. And then we'd get a bunch of features done, and we'd have a huge QA cycle where we're just attacking bugs. And you'd find that if you're doing test-driven development, these QA cycles are a lot shorter because you're essentially building quality into your code. A lot of times, sometimes I won't even test the code I write on a device when I'm writing Android apps, because when I'm doing TDD, I just know it works because my tests tell me it works. So sometimes I don't even need to run it. I have that much confidence where I can write the code, and then I'll push it and tell the QA guy, go ahead and test it. And he'll come back and say, it works perfectly. So it gives you a lot of confidence in what you're writing. Changing the code, if you don't test first, becomes very hard, because everything is so tightly coupled that trying to unravel one piece of the system starts unraveling all these other interchanging pieces that are very tightly coupled together. So it's very hard to change just one thing in the code without having to change multiple things. So when you test first, you tend to write the simplest thing possible to make the test pass. This is kind of the opposite of what people do when they write code. They kind of think, oh, it would be nice if my code did this, and I can build some sort of framework and do all these cool things. And you might find out that that framework that you wrote, you wasted a bunch of time, because that really didn't meet the business need that they were expecting. A lot of the features you wrote aren't being used. You have a bunch of dead code. Or you might figure out that your framework just sucks after a while of using it, because you thought it might work that way nicely, but you haven't. After a while of using it, you figure out, well, this isn't so great. So then you end up with those refactoring tasks. Hey, we got to refactor this code. It's not so good. And then you spend a lot of time doing that. So another thing is tests not only are testing that the code does the right thing. Your tests actually become, they tell a story. They're a specification of of what the code actually does. If somebody wants to understand how your code works, all they have to do is look at the tests. A lot of open source projects, they use test-driven development. Like, I'll make a plug for Square while I'm here because I love their libraries, but they kind of have a minimal documentation to their stuff. And that's because all you have to do to figure out how their stuff works is to look at their test cases. And that's what I tend to do whenever a library comes out. I'll look to see if they have tests written, and then try to figure out how the code works from there. So if you're doing, if you're doing TDD, you're kind of working backwards. You are defining the API first, and then you're doing the implementation later. But most people kind of do the code first, the API first, like, I'm going to design this grand architecture, and then kind of move things around, and okay, well, I could turn this into a method or whatever, and then the API is just incidental. Okay. So why should you test drive your code? So who wants their job to be easy? All right. Everybody should have raised their hand. Okay. This is why I push test-driven development, because I'm selfish. I want my job to be easier. So obviously, if you're working on a team, you have to write code with other people. So there's other contributions to your code base. So I would like those people that work with me to make my job easier. That's why I push this. And it is much easier for me to understand your code and to build on existing code that's written and debug code and basically get more done if it's test-driven. You might think, well, how am I going to be more productive if I'm having to write, code? I'm writing double the code or something. I have to write tests and the code. You'll find out in practice that that's just not the case. You actually become more productive. You don't have those long bug cycles like I mentioned earlier. And then I mentioned kind of executable specs. So your tests become a story sometimes I see tests written like test radio, and it's doing a bunch of stuff. And like, what does test radio mean? I don't really understand what you're testing, and you kind of have to look through this big hunk of code to figure out, okay, well, what are they actually testing? Whereas something like this, I can clearly see what's going on. I click on the power button, and it should turn the power on when the radio is plugged in. It seems pretty straightforward. So how do we do this? How do we write code that is hard to test? Does anybody know how you write hard to test code? Singletons? What?
Tightly coupled code.
Oh, tightly coupled code. How does that happen? Okay. If you have a lot of global state, your code becomes tightly coupled. Doing work in constructors, this is a problem. How am I going to test something that when I call the constructor, makes a network call or hits the database, does something like that? I have no control over that. Using statics is a problem. A lot of people like to use static utility classes. There's kind of a caveat to that we'll talk about later. Singletons. Now, singletons are a problem because they're essentially global state. I'm talking singletons with a big S and not a small s. What that means is the classic singleton that we all learned, where you have a static global variable that we assign an instance of the object to, and we have a static method that says get instance, and that's how we get our singleton everywhere. I can show another way to use singletons after, if you're interested. Using new. So who would have thought, right? You want to get an object you call new. Why is that a problem? You probably do this all over your code and never even thought about it, right? But it is a problem for testing. And then we have violating the law of Demeter, and we'll talk about that later. So let me get into dependency injection. Has everybody heard of dependency injection? Not that many people. Okay, so dependency injection is something you can use to write testable code, write loosely coupled code. So dependency injection is very simple. A lot of people make it more complicated than it needs to be. It simply means expose your dependencies in your constructor and pass them in. So don't new up all your dependencies in the constructor and not pass any arguments. So show your dependencies. So here's one way. Like I said, this might seem completely harmless, but this code right here is not testable. And that is because I newed up an engine and a transmission in the constructor of the car. So that is not dependency injection. However, this one is. So the car has a dependencies, engine and transmission, and they are passed in. We'll see how that benefits us later. So that is one thing you want to do. I'd like to attack a couple of myths surrounding dependency injection, because now you might be thinking, well, now I have to pass everything into my constructor. So now my constructor is going to just blow up and be huge, and that's going to suck. I could have just newed these things up and been on my way. So you might be thinking something like this. So I have a car with all these dependencies, and I got 9 here. It could be more. It's just an example. But that's a huge parameter list for the constructor. So that's a myth. What this points out is that there might be some logical grouping that you're missing on your class, or your class is doing too much. So some of these objects could be grouped together. So here's an example where the powertrain elements were grouped into a powertrain class, and then that is passed in. So let's see myth 2. Now I'll have to pass my dependencies through classes that don't actually need them. So I have some class A that has dependencies B and C. I've passed those in, but now I have a D in the do something method that requires an E in its constructor. But my A doesn't actually need an E. But since I newed up a D, I have to now pass that E in the constructor. So you can either do that by field assignment, save it as a field, and then use it when you new up your object, or you can pass it in where it's being used. This is a problem of confusing who should be doing what. So with this, what the object of dependency injection is to get rid of all the new operators in your code. And you move those to a dependency injection framework like Juice or Dagger. Has everybody heard of dependency injection frameworks? Heard of those? So what these do is these frameworks take care of creating all your objects for you and building your object graph. And you won't have to do things like new up a D, all you'll have to do is ask for a D, and it will take care of getting an E for the constructor, and it'll just pass you a D, and A will not have to know anything about it. So let's move on. Dependency injection containers. So these are the things that wire your application together. So your application, your code should be either in the business of writing the business logic of the application, or it should be it should have all the news in it. It should be either constructing the object graph or using the objects from the object graph. So Dagger was written by Square. It uses the standard javax.inject annotations, and it builds on that. It includes an annotation processor, and this will validate your modules and injections at compile time. So you'll know that your object graph is okay when you compile your application. There's other ones, which I won't mention, that use reflection, and the problem with that is a lot of times, well, all the time, you don't know if your graph is okay until you run and hit that part of the code that actually uses that dependency. So I highly suggest using Dagger if you're going to use a dependency injection container. So at the heart of Dagger are these modules, and what these do is, you see all the news here. So you'll notice there's an annotation that says app provides on every method. So the modules are essentially these objects that tell Dagger how to build the object graph. So what you're saying in the first one is, whenever you ask for a powertrain, return that powertrain there. Whenever you ask for an engine, so I made this Corvette specific. You can provide, so you want to code to an interface, first of all. You'll notice that we are passing back kind of an interface for each one. So engine is just engine. It could be anything. In this specific instance, it's the LT1. Transmission, we've chosen 7-speed manual. And what's cool about this is you can have different modules that provide the dependencies, provide completely different dependencies. So you can make a Corvette module or a Porsche module, and they can hand back different implementations. And the code running underneath doesn't have to care about what type is running, as long as you've written your interfaces in a nice way. So this is, the modules are the part that tells Dagger how to build the object graph. So how do you use it? So here's an example of how to use it. We've got the car class, and Dagger requires you to have the @inject, javax inject annotation on your constructor. So you'll see on the car constructor there's an @inject. And you remember previously in the module, we've told it when it asks for a car and that requires powertrain, paint, and frame, we've already told it a way to do that. And then the next module is one, you might have like a car game or something, and what you can do, you can have modules include other modules. So one nice thing to do is just to have one module that includes all your other modules. Then your entire object graph can be validated at compile time. There are ways to get around compile time validation. I don't recommend them by setting these things as a library. You can look at Dagger for more details on that, but I don't recommend going that route. It'll make your life a pain. So if you look down at the car game class, in the main method, what it does is it creates the object graph using the game module, which includes our Corvette module. So now it knows how to build cars that are Corvettes specifically. So when you ask for a car, you're going to get basically a Corvette. So you create the object graph. Then the second line in main, it creates the car game. And that's the point that bootstraps injection. So when you ask it to get the car game class and the game module is hooked up, it knows how to create your graph from that point, and it does it. So when when you get your car game back, it has, you notice there was a, here, let me go back. What was it? No, not that one. No. That one, okay. There's an add inject, the second line of the car game class. That car variable will now have a Corvette. So then when you call run here, you have the car at that point. You don't have to new it up. It's been created for you. So let's see an Android-specific example. So there are several places you have to bootstrap injection in Android. One place that's typical is the application class. So kind of the same code where you create the object graph, and we're doing it in onCreate. So that gives you an object graph object, and you can use that to do your injections. You'll notice get modules is returning an Android module. That might have some specific things for injecting certain Android classes, things like that. Another point to bootstrap is the activity. So I actually pulled these examples from Dagger's Android examples. So if you want to look at them and play with them and run them, just check out that code and play with it. We built, what's nice is you can build pieces of the object graph kind of incrementally. So you can have one portion of the object graph that is kind of global. That's the application portion. And then as your activities come on, you can kind of just build pieces of the object graph that you only need for that specific purpose, for that activity or the fragments within that activity. And you do this by using the, you can say dot plus on a different, see how we get the application graph, and then you can plus onto that some new modules, and now this gives you an activity-specific object graph that is an extension of the application graph. And then when your activity goes away, then that specific graph is out of memory. So you're a good memory citizen. Here is how you would use that last class to do injections into an activity. So I said previously that you should pass all your dependencies in the constructor. Well, Android doesn't play nice and give us the opportunity to do that. So you have to do field injection. So you would have to trust that when you called super on create, your injections happen, and now your fields, like the car up above, are instantiated. So how do you do TDD on Android? Seems the only way to do test-driven development on Android is to use Roboelectric. And what Roboelectric lets you do is lets you run Android code on the JVM. So you can run your unit tests within your IDE, and you can also have your unit tests run as part of your continuous integration. Excuse me. Because trying to run your test using the Android testing code, it's kind of slow. You've got to start up the emulator, and then you have to deploy your APK, and you can't really work that way. If things take too long, you're just not, I'm not going to want to write tests if I have to sit there and wait every time I want to run a test, because the cycle's supposed to be quick. You're supposed to write a test, write some code, write a test, write some code. And while you're doing that, you're continuously just running your tests, running your tests, running your tests, and they run within a matter of like a second. So if you have to wait, you're just not going to want to do it. So an example of how to do Android-specific at testing with Roboelectric is you have to use their test runner. And what this does is, they say it defangs the Android SDK. Basically, the Android jar that you get, that you build against, has no implementation inside of the method. So everything throws a stub exception when you call it on the JVM. They had a complicated thing that they used to do, but now they have the, they're using the real Android jars, but there's still some things that they mock out underneath, like the C code that would be device specific. Implementation details that you can't run this stuff on the JVM, so let's keep going because I'm getting over on time. So the first line lets you get a copy of the activity. You just tell it the activity class. You call create. That calls on create. And then you can go ahead and just use it how you would write code. If you want to find a view by ID, you just find the view by ID. It gives you the button, gives you a text view. And then you can perform a click and then make an assertion that something happened. Should I stop or should I keep going? Because I'm at 30. Keep going? Can we go over? Okay, we'll go over time. Okay. I want to talk about unit testing in particular and what constitutes a unit test. So a unit test, well, a test is not a unit test if any one of these things. So if it's talking to a database, it's not a unit test. If it communicates across the network, it's not a unit test. If it touches the file system, it's not a unit test. If it can't run at the same time as any of your other tests, it is not a unit test. And if you have to do special things to your environment to run it, it is not a unit test. The reason for that is a unit test focuses on a single unit. Most of the time, it's a single class. So if you have a class who has a dependency on a database, and you have database code running, you're no longer focused on just your class. You're also kind of focused on some other class's implementation details that you shouldn't worry about. So how do you get those real objects out of your code? You can use a mocking framework to provide mock objects, or you could just roll your own and write your own mock objects. Usually people will extend the class and then override methods, but mocking frameworks make it nice for you. Plain old Java code, you don't need to use Roboelectric to test plain old Java code because Android's not involved. So you can just write plain old JUnit tests, and the whole test suite could include both the plain old JUnit tests and the Roboelectric tests. So they could all run at the same time. It doesn't really matter. So Android code can kind of be a mix of unit tests and integration style tests, and they can all run on the JVM. So I'm going to talk about a specific mocking framework that you can use called Mockito. And so we'll talk about what mock objects are first, so we have an understanding of these before we move on. So mock objects are just a simulated object and mimics the behavior of real objects in controlled ways. So what does that mean? I think a code example we can kind of see in a second. Used to test the behavior of some other object. So you don't, like I said, you don't want to be testing, if you're calling a database or something, you're kind of dependent on the behavior of some other object, and you don't want to do that. You want to focus on the class you are currently testing. So the mocks allow you to focus on that class. Here's an example. So date code, if you want to get now as a date, when you call new date, what does that give you? It gives you system current time millis. When you run your test, is that predictable that you are going to get the same time every time you run the test? No, so you cannot test date-related code without doing something. So we create a date time class, and that just wraps the new date get time call. So if you want now, you would call datetime now. Say we have a date formatter, specifically middle endian, and you call format with the date. And this will give you the middle endian representation of the date. So how do I test that? What you could do, if you look at the bottom at the middle endian test, is you could create a date and set it to a specific date. So if you call date 0, you get January 1st, 1970. And then you can create a mock of your datetime class, and you can tell it, when now is called, then I want you to return epoch.getTime. So then you can run the test, that's the last line, assert that middle endian.format epoch is equal to. So what you've passed in here is a mock object. And you are testing, basically, that the format call did the right thing. An Android-specific example, going off the last example, say you have a text view that shows the current date. What you could do is something like this. You can inject the date formatter and the date time. And when you inject them, either through plain old dependency injection, pass it in your constructor, or unfortunately, Android kind of makes it hard to pass things in constructors. You can essentially pass in your mock objects and have the mock objects running inside of your code. So you could write a test around this that does the same thing as our last test, but this one is using the current date view that you saw on the last slide. And let's assume that your injector knows how to inject the fields inside the current date view. And you can just run the test, assert that the view has the right text. You can pass in the, okay. Okay. There's some subtleties to when you should use the new operator. Because we said new was kind of bad, right? You don't want to put news in your application code. Well, that's not 100% true. It depends. It depends on what type of object you are newing up. So it said that there are two types of objects. There's injectables and there's newables. So injectables, the rule is injectables can ask for other injectables, but not newables. And newables can ask for newables, but not injectables. So what are these things? So an injectable are the things that your dependency injection framework give you. All the news are in your modules. Examples of classes like these are service type classes, like credit card processor, music player. Newable are things that your DI container cannot give you. These are like data type classes, like credit card, song, and user. So you don't want to do something like this. You're passing your dependencies, and you are mixing an injectable, which is audio device, and a newable. But you're passing them into music player, which is an injectable. Your DI container will not know how to construct this object because it needs something you don't have when you're constructing it. So if you need the song, you can pass it in a method. That would be better. There's confusion around what dependency injection means. Inject annotations, not dependency injection. The dependency injection containers are not dependency injection. These are just factories for writing your application graph. I'm going to skip that one. I'm going to skip that one. Okay, let's talk about law of Demeter. So one thing you don't want to do is pass in some sort of like context object, or you don't want to pass in things that you don't immediately need. You don't have to reach through another object to get what you're actually interested in. So that's the law of Demeter. In a nutshell, you should only use one dot. So only call one method. Don't say get this, get this, get this. So breaking the law of Demeter is like finding a needle in a haystack. If you have bloated setup code in your test, that's a really good sign that you're breaking this. So you might have a test. You might have some code that does something like this, passes in a context and then gets lawnmower, get engine, get piston, get spark plug, whatever. So your setup code would get very big like this. If you want to. You also create an API that lies, right? You said clean spark plugs, but you're passing in a context. You have to actually look inside the code to figure out, well, what does it actually want? And I'm going to wrap it up with that. I'm going to hand it over to Marcello.
All right. Hello, everyone. My name is Marcello Hernandez. I work at Twitter. I'm currently on the mobile automation team for Android. So today, we're going to go touch up a little bit more on the on-device Android testing. Thank you, Christopher, for touching up on the test-driven development to make running unit tests faster. We're going to talk about Android's instrumentation test framework, though, where you can run tests on the device. So talk about why automated testing matters. We'll touch up on the Android emulator with the Intel HackSim. We'll have a quick demo that I've recorded for showing automation running on the emulator, just so you can get an idea how this looks. Talk about the Android test framework, instrumentation tests, a little bit on the Gradle build system, just so that when I don't put Gradle-specific stuff, you're not looking at me like, well, what is this? So we'll talk about testing libraries, testing applications, and, well, the items are there. So why automated testing matters? Well, as you can see, this is taken from my SDK manager. There are a lot of different APIs, right? Now, for those of you who don't know, Android has several different naming schemes for their versioning. You have like the major, traditional major and minor, and then they also go by API level. And the yummy part is they also use the dessert names like Froyo, Kit Kat, Jelly Bean, and so on. Gets a little confusing, but once you've had some time in developing on Android, you get familiar with these names. So we have all those different APIs, right? Then we have different OEMs, right? And they manufacture many devices. Each device can support X amount of Android APIs. So you can see how this test matrix can grow rather quickly. So bear with us, but you're about to enter right now the Android matrix. So this is what ends up happening, right? We say, all right, we're going to go test everything. We get devices from different OEMs. We get all the different API flavors. Our happy QA engineer goes on testing happily. Great, right? So let's be honest. That can be tiring. I mean, humans, we get bored. We get tired. We have emotions, right? Machines do not. They can do this millions of times for however long you want. So we need to be able to catch regressions immediately, and obviously manual testing can be tiring, it can be monotonous, right? So, and not only that, if I'm a QA engineer, I want to catch the more interesting bugs, I want to catch like, while the network connectivity gets turned off, I rotate the device while signing in, like those are more interesting bugs. I don't want to have to, every time a dev submits a change, check, does this click work? Okay, the app works great. No, that should be automated. So we're ready to write tests, right? We're ready to write automated tests to run on the device. So I'm a developer, right? Just plug in all these devices, right? Good, right? And my workspace is precious to me. So what else could we use? Right? We don't want to do this. The stock Android emulator? Yeah, right? It's pretty good, right? How many of you had experience with the emulator before, right? Right? You're just like, yes, awesome. I could put in API 19, 18, 17, good to go. We started up and man. Yeah, back to devices, right? They're a little faster, right? I wonder if there's a better solution alternative. Whoa, hardware acceleration. Does this exist? Yes, it does. Thanks to Intel with the HackSem plugin, we can install that and basically enable hardware acceleration on our emulators. Use the host machine's CPU and the GPU as well. So let's just talk about getting this set up for a sec. When you install the Android SDK manager, right, you have this option. So you have the traditional ARM system image, that's known as the slower version, and then we have the Intel x86 Atom system image. Install that guy per API version. Then on top of that, we look down in the extras section, and there's the HackSem module, which install that in to enable using the host CPU and GPU. When we configure our emulator, here's the GUI. We specify the CPU, right? The Intel Atom. If you have the ARM image, you can also select that one, but we want hardware acceleration. And then also, that little checkbox at the bottom is important because it uses the host GPU. The rendering is not done at the software layer. So allows your emulator to run rather smoothly. All right, so we're talking about all this automation running on device. You guys want to see something actually running, right? I mean, right? So here's a sample demo I recorded of using the Twitter app, automating our search tests. So we have the emulator running. We search Bill Gates. Well, we're just checking the list. That's one test. Go here, but basically it's verifying the UI, swiping through, executing code, done. Now I don't know about you, but I think that ran much faster than what I could manually, and that would have been quite tedious doing that every single time a check-in comes in. So Android provides this test framework that comes with the SDK, and these tests are based on JUnit 3. How many of you are familiar with JUnit in general? Oh, awesome. Well, unfortunately, we cannot benefit from the JUnit 4 at the moment, so we'll just touch up on JUnit 3 for a sec. Most of the classes that come in the instrumentation test framework, which is what it's called, it lives in this android.test package. And these are just a list of the test cases that you can subclass to test your specific Android components. The names are quite self-explanatory. I will say that the Android test case and instrumentation test case are sort of sibling classes. They directly subclass from JUnit's test case class. So a brief rundown on JUnit 3. You have your test case class. The runner will call setup for each test, run your test, tear down, reconstruct the class again, and run your next test method. You have to be mindful of this. Tests need to be able to create the state and properly clean up, which from Chris's talk, when we introduce too much global state, you can see how it's hard for tests to be able to reset the global state. That's why we follow the best test-driven development practices to make this easier. So what is instrumentation, right? You're hearing this word. It's this class defined in the Android SDK that basically allows you to monitor the system interactions with your app. So those of you who don't know, the view in Android, the activity, you can't actually instantiate it yourself. You sort of just tell Android, all right, start my activity, and then Android goes, creates it, and calls the lifecycle events on your activity. You're a little out of, you sort of don't have the fine granular control with instrumentation tests. But the nice thing with the instrumentation instance is you can call some of those APIs, like you can tell your activity, call the onCreate, the onResume. You can tell the activity to rotate, so you can test now landscape versus portrait. So as far as the tests go, they run on the device and or the emulator. Then the instrumentation test itself, it runs on a worker thread, not on the main UI thread, so you don't want your test actually hanging the UI. Though there are hooks, thanks to the instrumentation instance, that you can post a runnable on the main thread when you need to run certain actions on the main thread. Tests themselves are built as a test APK, just like your application is its own APK that gets installed, you have to make sure that the test APK is installed in order to successfully run your tests. And then thanks to the new, well, what I'll talk about next, the Gradle build system, which is what Google has been moving towards, you can actually test your libraries in isolation. So when you start off with a basic Hello World Android application, you might just have all your logic in one project and that's it, your UI, your core business logic, i.e. the Hello World statement. But as your app begins to grow, become more robust, it's nice to make it more modular. Separate your core business logic into a library. Perhaps you may create custom views that can be reusable, separate library. Finally, you have your application module, your project that depends on these libraries. Should you really have to start your application just to test the libraries? No, it'd be nice if we can sort of run our own unit test or component level test on our library, and then finally run the UI test on the full application. So just a quick rundown on Gradle. It's like the successor to the traditional Ant-based build. Anybody even played with Ant before? Okay, there's a build.xml file that you have to define, and it defines all the tasks, and it's a lot of clunky XML. So think of build.xml, right? It's to Ant as build.gradle is to Gradle, except Gradle uses the Groovy language. So for those of us who prefer using more of a scripting language, more of a programming language for defining your build, I prefer that over XML. And then the way it works is you provide Gradle plugins that define a set of tasks, kind of like your Ant tasks. So if you were building just a standard Java application, there's a Java plugin for that, which defines tasks for compiling, building, running tests. And then Google has sort of extended that and created the Android Gradle plugin, which you see now if you ever use Android Studio, they use that. So the Android Gradle plugin defines plenty of tasks, and some of them are even similar to the Java plugin. So here's a traditional, here's a typical Android project that uses Gradle. You have everything sort of in this project root, and then you have your sub-modules or sub-projects. And each directory has a build.gradle. So you can have a root level build.gradle that has a bunch of tasks that apply to the entire project, or a build.gradle, and also build.gradle files within each sub-project. So you can invoke project-specific tasks. And you have this Gradle W file, which is the Gradle wrapper executable that runs Gradle. So you get a little familiar with the structure here. So when you run tasks, it's Gradle W and then the task name. That will execute a root level task. But if you want to target it at a specific sub-project, it's colon the project name, colon the task name. So we're a little familiar now, right? How to execute some basic tasks. So in the case of installing an application, say your app project is known as app, you would run the install debug. This will initialize the install debug task, which will then, it has a set of dependencies on other tasks. So it will go and say, hey, I need to install, okay, great. Did we compile yet? Okay, no, execute the compile task. Well, go on. And then finally it will go up, check if the device is connected, and then install the APK. Running tests, similar, is a connected check task. So this will check, all right, is the device connected? Great. But before that, it'll go and run the other tasks like compile your test. Well, in order to compile a test, I need to compile the source, and so on. If Gradle will detect if it needs to run those dependency tasks as well. So the nice thing is with Gradle, you can test libraries in isolation. So in this case, we would run the library connected check task. And this will actually compile your library into what was known as an AAR file. And then the Gradle plugin system will actually generate a test wrapper APK that builds a dependency on your AAR and actually install the test APK on the device. So think of it as like a test application that just consumes your library. And then it actually runs your tests on the device. So it's one APK that gets installed, and then Gradle will uninstall it. But when you want to test applications, here's the thing that gets some people that it's not obvious, but there are two APKs, the app APK and the test APK. And in the case of the my app connected check, it will actually go and build the app, install the APK of the app, build the test, install the test APK, and run. And then your test APK will target the application and run tests. So We touched up on unit testing before. In Chris's slide, he talked about Roboelectric and running unit tests on the host JVM, but just want to sort of give an example of how an instrumentation test runs on Android. Instrumentation tests can run from simple unit tests to a complex UI test. They're all instrumentation tests. So let's take, here's a sample test for this tweet parser class. We instantiate the tweet parser, and the thing is, our test extends Android test case. So Android test case is one level below its subclasses, the JUnit test case. And this gives you access to the application context which your class might need. In this case, tweet parser's constructor takes in a context. For whatever reason, the implementation uses some context-specific APIs. We can get access to that context just by subclassing Android test case. So here we'll set some JSON and we'll run our assertions. Simple. Say we need a little more than just the application context though. We need access to instrumentation. We need perhaps access to the test context. Tests have their own context. You can actually check in static resource files that just live within your test project just for testing purposes. We can get that by subclassing instrumentation test case, which by subclassing that, we have this get instrumentation method. We get the access to the instrumentation, and now it gets a little confusing, but worth calling out. Get target context will give you the application context. Get context on instrumentation will return the test context in this case. A little confusing, but yeah. So say we have this custom tweet view, right, that subclasses the Android's view, and we construct it with the application context, right? But now we have just some localized string resource that we check in on the test side. We don't want to hard code in our strings all the time, so we can use a test context to resolve the string resource. Now let's say our TweetView class has a setContent method, and we specifically check that if you call setContent outside of the main thread, throw an exception. Well, remember, instrumentation tests, they run on a background worker thread. How do we get around this? Oh, thankfully, instrumentation has this run on main sync API. So we can run on main sync, pass in the runnable, and now run our setContent on the TweetView. The instrumentation will take care of blocking. It will guarantee that that runnable executes before executing the next line, so you're not dealing with concurrency issues. You can safely run your assert right after that. So generally, I like to sort of tell developers that when try to think of your activities sort of as like your view, and then you have your core business logic in other classes, but sometimes we do tend to cram business logic in our activities, and may be worth unit testing those activities as well. Thankfully, the Android SDK does provide some activity-specific test case classes, and these are either direct or indirect subclasses of the instrumentation test case, so you still get access to instrumentation. These are a few. I'm going to touch up on activity instrumentation test case 2, though, because you'll see later on that many of the UI automation frameworks, they build on this class specifically. A lot of their samples show that. So we have this Android Fest activity test, right, that tests this Android Fest activity, right? And then the thing is, we have to make sure that our test sets up and tears down appropriately. With instrumentation tests, with activity instrumentation tests, I've noticed that if you do not explicitly kill or sort of clear the activity stack, the next test will hang. You have to make sure to explicitly finish that activity. So we'll get a reference to it in the setup. The first time we call getActivity, the activity will actually launch on the screen, render, and any subsequent call will just return that instance. In the teardown, we finish it and then call super.teardown. Now here's the gotcha with activity instrumentation tests. If you call super.teardown before your cleanup logic, the super class will actually null out all your fields. So if we were to call mActivity.finish afterwards, we'll actually run into a null pointer exception. So keep that in mind. So we have a test default location, and our Android Fest activity has a get event location. We want to test it by default. It's Santa Clara, California, right? Great, test passes. Now we want to interact with some of the components. There's an edit text field. Based off of that string, it will dictate what get event location returns. We want to test that when we set the text of that edit text, that get event location now returns the new string. Now, set text on an edit text should be done on the main thread. Views generally are interacted with on the main thread. So, get instrumentation, run on main sync, set our text, run our assertion, good to go. So, that was basic instrumentation testing, but now we want to test the UI. Now imagine if running your UI is, basically your UI tests are getting references to views, calling set text, calling perform click on a button. It's not actually doing what the user would do. They're sending, gestures, they're sending tap events. Okay, so now we have to use the motion event classes, we have to use some more low-level APIs and sort of simulate that. It's a lot of code right there to write. So thankfully, we have frameworks that wrap this. Anyone ever heard of Robotium? A few hands. It's one of the, say, industry-leading UI automation frameworks, so there are others that are also coming up. Basically, a robust set of APIs. You have some, you're able to get, you're able to search views by ID, text, class type, etc. You can call clear text on an edit text. You don't have to actually worry about clicking on it and pressing the delete key or anything like that. You're allowed to, there are plenty of waiter sort of methods where you can wait for a view to appear. You can wait after you click a button, wait for your activity to launch before invoking the next action. And lastly, there's a conditions interface, which you can define your own custom condition to wait for as well. And then the nice thing is, remember how I mentioned when you tear down, you need to actually clear out the activity stack? Well, with Robotium, it keeps track of it for you. So you just call one API in your teardown, finish all open activities, takes care of it for you. So here's some sample Robotium code. And you can see here that we're trying to get a button, right? So we get the next button. Now we do a click on it. But we can't just assume that the activity has transitioned over to the next one. So we say wait for activity. But perhaps the activity didn't launch. One practice I like to enforce is wrapping your wait for, because they return Booleans, wrap them with an assert true, so that you know if the activity never came up, the test will fail immediately as opposed to executing the next line of code. And now you're sitting wondering, why did my test fail? It's pretty clear right there that if that assertion fails, the activity never started. So now the next activity comes up and brings up a series of progress bars because we're loading content, right? It's not safe to just try to click on a button in the next screen because it may not be visible yet. So here's an example where we use a condition, and we would override the is satisfied. Right here, I haven't included it, but you get the picture. And then we define a timeout, and then we can say wait for condition. And Robotium will go and check the is satisfied condition. It will poll on that condition. Then we assert that we have this, say there's a text field in the next activity, we can assert that the next text is there. Now let's think of a more real world scenario like a tweet view, right? We can get a tweet view. We can assert that it's not favorited. Then we go on and get the favorite button of the tweet view. We click on the favorite button, and now we can assert that it is favorited. Simple test. So you've seen some sample Robotium code. I mean, those were very basic, but as you can see, if you want to write non-flaky tests, you have to make sure that you handle all the timing conditions. So the pros are there's a large user base. Many companies use it. It's been around for a few years. It's rather stable now. It supports Android 2.2 or AKA API 8 and up. And you can also, it can become a little more on the white box side of things where you can access the views, the activities, and actually invoke APIs directly as well if need be. The cons though, you end up writing a lot of boilerplate polling code, wait for code, just to make sure that your tests are not flaky. The fact that you're running your UI actions on a background thread versus the main thread can sometimes introduce some flakiness as well. So you end up writing a lot of a lot of boilerplate code in these runnables that then have to get posted on the main thread, so on. So here's a new framework that's coming up, been built in-house at Google by a team known as Espresso. And Espresso sort of extends, it realized some of the features that the default instrumentation test runner lacked, like being able to keep track of the activity stack and clearing it, and they subclassed it and created the Google instrumentation test runner. So if you're using a project that you're going to write your automation in Espresso, you need to use the Google instrumentation test runner, which is also compatible with normal unit tests and even Robotium-based tests. So you can even mix them. It's a little more black box in the sense that you cannot wait for an activity, you can't wait for a view. It's basically testing what the user sees. So if you need to assert that you're in a new screen, you need to assert based off of the views, based off of like the text that you see or a button. The nice things about it is Espresso actually synchronizes on the main thread for you, as well as the default async task thread pool. This is huge because now I don't have to worry about waiting for things to happen. If the UI thread is not idle, Espresso will just sit back and wait. It will basically say, it will constantly keep asking the UI thread, are you done? Are you done? Oh, you're done now? Okay. Run the next action. Perform the click, the swipe, the scroll, whatever. It also leverages Hamcrest. Have any of you ever heard of Hamcrest before or used Mockito even? Not many, oh, a few hands. But I won't go into too much depth, but Hamcrest is this powerful matching library, so you can define custom matchers, which Mockito is built on top of, and Espresso also built on top of. I'll show you a little sample. So here's the previous test, rewritten using Espresso, and I added a few comments just to make the code look a little longer. So as you can see, it's pretty expressive on view, with ID, perform a click. And then the Espresso will realize that, okay, the activity is now transitioning, so the UI thread is no longer idle. It will sit back and wait, because when the next line of code executes, what that's actually doing under the covers is posting that action basically on the message queue to be run whenever the UI thread goes idle. Now we say on view with text, and we can use the actual string resource ID. Espresso will resolve it for you, so it's great for localized testing. And we can check that it is displayed. And you can see a little bit of Hamcrest right here by when you see matches is displayed. These are all sort of custom matchers that are built on top of the Hamcrest matcher libraries. So one can actually extend Espresso to sort of cater to their needs. And let's just take the Twitter app, for example. We can actually extend it to define our own Twitter-specific matchers. And you could have a test that does something like this in the case of the favoriting test case. On view with ID, check that it's not favorited, perform the favorite action, and then check that it is favorited. And the nice thing is you can actually write more expressive sort of chain-like style coding. Pros of Espresso, supported in-house by a team at Google, which makes me more confident that bug fixes will be addressed as future versions of Android come out. Google will update it, but nothing's guaranteed, but that's a pro. Supports also Android 2.2 and up. The style of code is it's clear, it's expressive, it's simple, which is great. You know, as a test author, you should be able to just write your test with minimal effort. By synchronizing with the main thread for you, you don't have to worry about all the boilerplate code of waiting for conditions. Also, constantly polling with Robotium, I noticed, will cause tests to take longer to run. That test that I showed before, the demo, the previous version, which was written with Robotium, took about 54 seconds to run the whole test because we wanted to make sure that we waited at the absolute right time to invoke the next action. With Robotium, it was with Espresso, it was like 15 to 20 seconds, so much faster. So the tests also tend to be less flaky, sorry. And as you can see, Espresso can also be very extensible. And the cons, it does sort of require that you use standard async APIs like the async tasks. If your application is newing threads, if it's creating a custom async service or some async operations, Espresso has no way of knowing how to wait for that. You need to be able to register that somehow and let Espresso know. And if you don't provide the hooks in your app, that can be a bit of a pain. So then some people might think that it's a con that you cannot access the activities or views directly. So it's up to your, sort of opinion based, but that can be a con. The fact that you cannot support any waiting or polling, that can be a con to some. I like the idea of actually being able to define an idling resource and letting Espresso know, here's another resource that you should wait for. And then another thing I've noticed with working with Espresso, when you're automating lists, it requires a deep understanding of the implementation of the list, the actual adapter that it's backed by. Perfect example, at Twitter, we have custom lists for our home timeline, our activities timeline. Each list is a custom list with a custom adapter, and quite frankly, I just want to know how to select a tweet with some match content. So we had to do some refactoring on our end to make that easier, to make it more Espresso friendly. Quickly touch up on UI Automator. It is completely black box. It comes with the Android SDK. These are actually tests that the code is compiled independently from the app source code. It's basically allows you to interact with any part of the UI. Now you might say, well, this is great. Why not just use this instead? Well, if you want to run a test that requires you to be signed in, you can't actually invoke the API directly within the app. It's running outside of the application process. So you have to actually manually write automation that signs in, gets the test in the right state, and now run the actual test. And then you probably should restore the state, right? Okay, automate signing out. The benefit of instrumentation tests is you can just call the API directly, sign in, now run the test, sign out. But with this, you can actually interact with system settings. You can go into settings, disable the Wi-Fi. You can check notifications. So basically, you pick the right tool. You should pick the right tool for your need. And I mentioned pretty much what I mentioned were the pros, the fact that you don't have to compile it with the source code. You can automate views that are outside of your application process. And the fact that you don't have access to the actual IDs, it helps you catch accessibility bugs, because if your app is not accessible, UI Automator has no way of knowing how to interact with it. Then cons, completely black box. I like to have some access to the code, so cannot make direct API calls. And at the moment, it's not integrated, I think, at all with Android Studio or the new Gradle build system. So for those of you who have moved on to those technologies, it's a little bit of a drawback. Then if you need to run your tests on multiple devices, each device has its own custom home screen, its own setting screen, so trying to abstract that out can be a little challenging. It's also only supported on API 16 and above. So for those trying to test 15 and lower, you just can't run the tests on them. And then on 16 and 17 even, you do not, UI Automator does not expose IDs for views. So running localized tests is even more painful, because you have to actually get the hard-coded string. You know, if you're running on English, then later on you want to run on Spanish, for example, you need to keep some track of some sort of dictionary yourself that you can find the right language. It's gotten better with 18 and 19 because the accessibility APIs actually reveal the ID of the view, so UI Automator can access that. So in conclusion, instrumentation tests. They're tests that run on the device. And they range from basic unit tests on a device to full-scale UI automated tests. Remember, you can leverage hardware acceleration on the emulator, so that alleviates the pain of running tests or even just testing on a slow emulator. Thank you, Intel, for the Haxum plugin. Then for UI automation, we have three main frameworks: Robotium, Espresso, and UI Automator. Then if you're wondering what we use at Twitter, right now we're currently favoring Espresso. We like the speed, the style. We're rewriting a lot of our Robotium tests into Espresso, but we still have plenty of tests that are based on Robotium. And then for other tests, like installing one version of the app, uninstalling, installing then a new version, and checking the upgrade, we call these our upgrade tests, we have to rely on UI Automator. Thank you.